Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem longest ideal subsequence. The hardest part about this problem is honestly just understanding the question, but we'll get to that in a second. So we're given a string s consisting of lowercase letters. So only consisting from lowercase a through z. That's going to be important in this problem. And we're also given an integer k. The idea is that we can call a string ideal if it satisfies the following conditions. One, that string is a subsequence of s, the input string. So we're dealing with subsequences. And usually when we're dealing with subsequences, the solution, especially for a non-easy problem, is going to involve dynamic programming. And that's because subsequences, which they define down here, lend themselves to dynamic programming because to get a subsequence from a string, you kind of have to make a choice. We can either include the first character or we skip the first character. We can either include the second character or we can skip the second character. And we do the decision every single time. And this just lends itself to dynamic programming. That's at least my thought process, though you might not be able to immediately recognize this. Now, the second condition here is honestly funny that they don't really explain it. They don't even explain it in any of the examples, which is funny because they literally tell us what a subsequence is as if we've never heard of that before, but they don't explain this part, which is the absolute difference in the order. So if we have a string t, so for example, so input string is this, and let's say the string t that we choose, just like in this example, is A, C, B, D. So this is a subsequence from here because we chose the first character, the second character, and then we chose these last two characters. That's how we got this. The order of these did not change. Now, the condition states that for every two adjacent characters in this string, the absolute difference between these two characters has to be less than or equal to k. So in this case, k is 2. Now, what's the difference between two characters? Well, you can kind of think of a mapping as if a is equal to 0, b is equal to 1, and then, all the way down to z, which is equal to 25. So think of it like that. And if you do, you know that the difference between these two is going to be 2. The difference between C and B is also going to be less than 2. It's going to be 1 because these are adjacent in the alphabet. Lastly, B and D, the difference between these two is also going to be 2 because that's the difference between them in the alphabet, right? So that's what this second condition is saying. It doesn't mean the sum of the differences has to be less than or equal to k. That's what I initially thought. So if this was confusing to you, this is exactly what it means here. So knowing all of that, I think implementing the brute force solution to this problem is somewhat reasonable. It's not crazy. So this is kind of the thought process behind the brute force solution. Let's just create every single subsequence that follows this constraint. How exactly do we do that? Like, this is the solution I have shown here, but assume we don't know that this is the solution. Let's just go through this input string. Let's try every possibility. We can either choose A or skip A. Okay, so we have a subsequence A and we have an empty subsequence here. Now, here we can either choose C or we can skip C. This is where it gets more interesting. When we made our first choice, it doesn't really matter whether we include it or don't include it. We're allowed to do both. But when we choose our second character here, we have to ensure that the absolute difference between this character and the previous character that we chose has to be less than or equal to k. K is 2 in this example. So we would not be allowed to make this choice if the difference was greater than k. So just keep that in mind. I'm not going to draw too much of this side. You can draw it out if you want to, but we already know that that's not where the solution lies, so I'm not going to waste too much time here. But continuing down here, so with C, now we get to an interesting choice. We can either choose F or we skip F. Are we actually allowed to do that? The difference between C and F, I think, is C, D, E, F. It looks to me like the difference is 3. That's obviously greater than 2. Therefore, we're not allowed to go down this path, so we don't do it, right? So now we skipped F. Again, we make the choice. Do we choose G or do we skip G? And again, the difference between G and C is going to be greater than 2, therefore we skip it. Eventually, though, I won't draw out the entire tree. We're going to get to B, and then we're going to get to D. And so we're going to find that the longest path we were able to create in this entire tree was looking like this. I didn't show this as I drew the tree, but there are a couple things we're going to keep track of as we do this recursion. And by the way I've drawn this tree, if we're going to branch 2 times every single time, it doesn't look very efficient. It looks like the worst case. This is going to be 2 to the power of n, where let's say n is the length of the input. Not super efficient, right? But let's just go back and figure out how we would implement this, because obviously if we're going through the input, we're deciding keep this or skip it, keep this or skip it, keep this or skip it. We're going to need a pointer. Let's call that I, which tells us what index we're currently at. So far we know that we're going to maintain a pointer I. We also clearly need to keep track of what the previous character was, don't we? Because consider this path where we, let's say, skip C and then we went down to F or something like that. To make it more interesting, let's say we skipped A and C and then we went to F and then we went to G. Obviously, this path is valid. Just because we had to skip G over here doesn't mean we have to skip G over here. And the reason for that is because the previous character before G, in this case, was F. The previous character matters when we're looking at the current character, which is determined by our pointer I. So let's have a second variable, and we're going to call it previous. It's going to be the previous character, or we could just, map that character to the number that it corresponds to just to make the math more easy for us. Doesn't really matter what we do, but obviously the previous character matters. If these are the only parameters that are actually going to be changing as we do the recursion for this problem, then we can use these parameters to improve the efficiency of our solution with caching. Because even though the size of this tree in the worst case is going to be 2 to the power of n, it's possible there's a lot of repeated work in that case. It's possible that, for example, here we skip the character and, well, I guess actually this example isn't complicated enough to illustrate this. So the better way to explain it would be the total number of possibilities here is that for every single character I, like for this character, for this character, for this character, the total number of previous characters that come before it is not going to be infinite. It's going to be up to 26 different characters that could have came before the current character. So instead of saying 2 to the power of n, the actual time complexity is going to be n times the number of possibilities for this, which is actually 26, our character set. So that's going to be the big O time complexity. And it's also going to be the big O space complexity because that's just how caching works with these parameters. I covered it a lot, I think, in my DSA courses if you want to check them out on Leetcode.io. But now let's quickly get into the recursive solution. And then after we go through the recursive solution, I'll actually show you the full dynamic programming solution, which actually improves the memory. This is the best time complexity we can get for this problem, but we actually can improve the memory complexity to be big O of 26. So let's get into it. With the recursive solution, I like to define my recursive solution nested inside the outer function. Then we don't need to pass in these variables, but the variables we are going to pass in, as we discussed, are I and previous. Now, the base case, we didn't really cover either, but I think it's straightforward because we're going to keep going until we reach the end of the input string. So that would mean when I is equal to the length of S. The other thing I guess I didn't cover in the drawing explanation was that we are trying to return the longest string, not just the string, but actually the length of it. So let's think about the base case perspective. If we have an empty string, what's the longest string that we can get from that? Obviously, it's of length 0. So that's what we would return in the base case. But in the general case, it gets a bit more interesting because, like I said, we have two choices. We either skip the character at index I or we include the character at index I. So this is how I like to think about it because it makes things pretty simple for us. Now, the skip case is almost always simpler because in our case, if we're skipping, then we'll call the helper function and we will go to the next index, of course, and the previous character that we had will not change. So in that case, we can set the result equal to this. This is our result so far. This is the maximum so far. Now, it's possible that including the character will yield a larger maximum. So let's get that. What's the formula for if we were to include this character? It would be calling helper once again at I plus 1, but now the previous character would change. If we're including the current character, then our previous character would become that character. So this is the recursive call for that case. But are we always allowed to do this, right? That's the question we're asking. Are we allowed to even make this call? Well, we'd only be allowed to do that if the absolute difference between the current character, let's say S of I, minus the previous character is less than or equal to k. Only in that case are we allowed to make this recursive call. And just in case you're wondering, ORD in Python basically gets the ASCII value of the character. And we don't care about the ASCII value, we care about the difference between the ASCII values. So this is just the easiest way in Python to basically make that mapping. It doesn't directly make the mapping, as I mentioned. It won't literally map A to 0, and it won't literally map Z to 25. It does it slightly differently, but the relative order of them will be preserved. That's all that really matters. Now, if we are allowed to do this, then we potentially want to update the result. We want to then set result equal to max of either itself or this recursive call that we are making here. And now you kind of see why I decided to put the skip case before. If we had done it in the other order, this part might never even execute, therefore result would be uninitialized. After that, we will down here return the result. And now things get a bit interesting because before I even add caching to this, I want to fix a couple things with the solution. And that has to do with how we call the helper function. We want to ultimately return what the helper ends up returning. We know we start at index 0. That's what I is going to be initialized to. But what about previous? Previous isn't anything. It's not going to be A or B or C or Z. So I guess one possible solution would be to set this to like an empty string here. There are other variations of doing this. Like there are ways to do it where you don't pass in an empty string, but I'm going to stick with this because I think it's relatively simple. And so now when we update this condition here, we can include the current character if the absolute difference between it and the previous is less than or equal to k, or maybe the previous character would be equal to the empty string in the first place. So that's just how I'm going to implement this. Because if we didn't have a previous character in the first place, of course, we are allowed to choose the current character. So that's the logic behind that. Now, lastly, we need to add caching to this to actually make it efficient. And so I'm going to create a hash map. That's what I usually like to do for caching problems. And then I'm going to check, is this parameter already been called? Is it already inside of the cache? If it is, let's just go ahead and return it. If it's not, let's go ahead and execute all of this. But before we return, let's make sure to throw the result into the cache just like this. So this is pretty much the entire code, but I do realize that there's one thing I did miss. Our result, as you can kind of tell from this, is never going to increase beyond 0 because I missed something. When we're skipping this, then we just make the recursive call. But if we include the current character, we make the recursive call, but we should also add 1 to that because that 1 comes from the character that we are including. This is the sub problem where we look at the remainder of the string, but if we're including the current character, we should definitely have a +1 here. So that's what I'm doing. Now let's go ahead and run this. And as you can see, it pretty much works, but towards the end of the test cases, we get a memory limit exceeded. I think if we really wanted to make this solution pass, we could change this to be a 2-dimensional array rather than a hash map, but that wouldn't really change the big O memory complexity. So I don't really think it's worth doing. Like in a real coding interview, there wouldn't be any difference between this solution and one implemented with a 2D grid. But there is definitely a difference between this solution and the next one I'm about to show you. So let's get into that. So with what we learned from the recursive solution, let's try to translate that into a bottom-up dynamic programming solution where we don't have to rely on recursion. We have here the example problem. I'll kind of write a blue line to separate that from what we have drawn here. So the same input string, k is equal to 2. I've drawn a 2D grid. So this is similar to the cache that we had in the previous solution, and we could have used a 2D grid for that, which is what we're going to do here. Now, if you go back and look at the previous solution, what we were doing when we were doing recursion is we were asking ourselves, what is the longest string starting at I, wherever we were? If we started at the root or if we were already halfway through, we're asking what's the longest string from here? And then maybe what's the longest string from this side as well? And among those two, we take the maximum and then return it. We can apply the same logic of finding the longest string starting from I, so starting from here, starting from here, starting from here, and starting from here, like all the way down. We could apply that logic, but if you're going to do it that way, you're going to end up iterating over the input string in reverse order. For some reason, people don't like it when I do that, even though it's more similar to the recursive solution. So I will, I guess, do what people prefer and iterate over this string from left to right. Now that requires changing the way we think about the problem though. That's going to require us to now ask ourselves, what is the longest string ending at this pointer, at this character? And the reason for that is because we're going to iterate from left to right. There's no way we can figure out the length of the longest string starting at this character if we haven't even seen the rest of the characters. So that's the logic. That's what we're going to do. We're going to iterate over this grid from top to bottom, from like left to right, I guess is a better way of thinking about it. But we're going to ask ourselves, what is the length of the longest string ending here, ending here, and all of those? And I redrew this part because if we're doing it this way, actually, in the general case, it might be easier for us to actually just zero out this row. So I won't draw all of those, but we'll zero those out. And now I'll kind of start to explain what this grid actually represents. We're going to fill this grid in kind of like this, from left to right, each row by row. What we do with the real first row, so assume this is kind of just defaulted, with this row, we're going to ask ourselves, what is the length of the longest ideal string that we can create ending with A if the previous character was A? And here we put a 1. I know that sounds kind of confusing because if the previous character was A, then obviously we have 2 characters, don't we? So shouldn't we put a 2 here? And this is just kind of to make the math work out. That's why we put a 0 here, because in reality, we're adding the number here to this, to including this character. And we're only doing that with A because the difference between these two is less than or equal to 2. And again, like this first row, when we fill it out, it's not really going to make a ton of sense because now we would kind of look at all of these values and quickly see that, okay, B and A have a difference of less than or equal to 2, C and D also do, but we wouldn't fill those values in here. We would only fill the 1 over here. So you can kind of assume the rest of these are 0. Now it'll start to make a little bit more sense. So with C here, we're going to do kind of the same thing. Okay, C, what's the longest string we can create ending here? Well, let's go through it. C and the character above A have a difference less than or equal to 2. So we'll say 1 plus that previous value. Okay, so then we get a 2. We would do the same with the rest of those. Even the ones that have a difference less than or equal to 2, though, are all going to be 0. From here, they're all 0. Actually, this 2 here would not go here. It would go here. Because if we include C, the character ending at C is going to be equal to C. So that's where we would put the value. So what this grid represents now, we can finally kind of talk about it. Let's say DP of I and previous represents the longest string ending at this index, not necessarily including that index where the character before that we actually included was this character. I know that's pretty confusing, but when you think about it, it's not that different from the recursive explanation and the recursive solution that we did. It's generally more difficult to implement it this way, so it's not surprising if this part is much more difficult for you, but just so you know, that's what this represents. One thing I'll also say is that this solution is actually more difficult than the more optimal solution I'm about to show you. So don't worry, it's actually about to get a little bit easier. One thing I didn't show is we don't need to put a 0 over here. We can actually take this 1 and move it down here because, like I said, just because this is the ending index does not necessarily mean we need to include this string. So what this 1 represents is that if the last character is A, then the length of that string would be this. This is what the string would be, and its length would be 1. If the last character is C, and we go all the way up until this point, the length would be 2, and it would be this string. Now, when we get down to F, we can put a 1 here, a 2 here, and wherever F is over here, there would be a 1, because from here, we would look at every single character, and none of the positions that have a value greater than 0 would have a difference less than or equal to 2. So this is if we do the two-dimensional grid approach. It looks pretty complicated, but the interesting thing about this is you notice as we fill in every single row, we only need to look at the previous row. We don't need to look 2 rows up or 3 rows up. We literally, to fill in this row here, we only need the previous row in memory. So now I'm going to show you how we can finally reduce the space complexity from what I've drawn here, which is n times 26. We can reduce that to just 26. Let me show you. The setup looks similar so far to what I previously had. We have an initial row, which I'm going to call DP. It's going to be initialized with all zeros. And this is what we're trying to fill in. We're trying to fill in, let's say, for the first position. So we're going to go through every position in here, and we're going to say, okay, so for this position, we're at currently the character A. Let's take the absolute difference between this. It happens to be 0. 0 is less than or equal to K. Okay, so the value we can put here is going to be 1 because we're including this character. We're allowed to include this character because the previous character is a difference that's valid. So we're saying 1 plus whatever the value here happened to be. Okay, it's just 1. We do the same thing for every one of these other characters. We find that only these two have an absolute difference of less than or equal to 2. So for each of those, we would say 1 plus that value, and we'd put it here. We'd say 1 plus this and put it here. We don't put those values here, remember? Because we're ending at character A. So we only put the value here. It indicates that we ended with a character A. That was the previous character, in other words. The rest of these would stay 0. So I think this is kind of what's confusing about this problem. This is why it's different from a lot of other dynamic programming problems, because even though we have a row here, we're not filling in the entire row. For all the other values that don't include A, we just take the previous value from the previous row. That's why this problem lends itself so well to flattening this dynamic program. We don't need the entire grid, we only need a row, because we're going to take all the previous values anyway. Therefore, generally when we have these types of problems, I create like a DP array and then I have a next array over here. I call it next DP. But in this problem, we actually don't need even 2 separate DP arrays, because like I just showed you, all the other values are going to be copied. Those are not going to change. So we don't need another DP array. We can modify this one in place because we're only ever going to be increasing the values at each of these positions. They're never going to decrease. They're never going to change unless they increase. So even though I've drawn it this way, just to kind of make it more simple to visualize, this is not how we're going to implement it. There's not going to be separate arrays. We're only going to have a single DP array. You can think of this as just me showing you the changes that we're making to the array. Next up here, for the value, we would look at pretty much every single one, and we'd find that this one, A and C, are technically less than or equal to K. So we'd add the +1 here from here, so we'd get a 2 in this position. For F, wherever that would be, so D, E, F down here, we would not find that we can take the 1 or the 2, so this would actually stay as a 1. And you might be wondering, where do we get that 1 from? Well, when we look directly up, we're going to see that 0 is at F, and technically F and F do have an absolute difference less than or equal to 2. I guess the same could be applied when we look over here, because E and F also have an absolute difference less than or equal to 2. So we would take that 0 plus the 1, and then we'd get a 1 here. So by the time we're down here, this is what our thing would look like. Everything else would be 0 in between these, but we'd have a 1 here, a 2 here, and a 1 here. If we were to continue with the rest of this, for the G row, we'd kind of skip it. Nothing would happen with that. But when we get to B, we'd find that we look up and we see this value. It's a 2. C and B have an absolute difference less than or equal to 2. Therefore, we add 1 to the 2, and then we get a 3. Lastly, when we get to D, we'd look up and we'd see B has the value 3. When B is the previous character, when it's the last character in a string, the length of that string is 3. And we also know that B and D have an absolute difference less than or equal to 2. Therefore, we'd add 1 to the 3, and we'd get 4. 4 is going to be the result. So that's how this works. Believe me, I know that it's complicated. I would encourage you to draw out the entire grid if you think it'll help you, but I don't think anybody would want to watch me do that for like an hour. So I will get into the coding solution now. So I'll leave this code here in case it's helpful for you, but I'm now going to get into the dynamic programming solution where we will have a single DP array of length 26, and it's going to be all zeros initially. Now we will have our result initialize it to 0, and that's what we're ultimately going to be returning, but we first have to fill it in. So let's do what I kind of showed earlier. First, we're going to go through every character in the input string. And I guess I could probably just iterate over it like this for C in S for every character. We're going to go through every previous candidate. So for previous in range 26, we could go like A through Z, kind of like we did below, but it's going to be easier to just think of it in terms of numbers here. So we're actually going to do the same thing. So if the previous character is a number, we consider every possibility, and we're also going to convert the current character into a number as well. The easiest way to do that is just get the ASCII value of that character and subtract from it the ASCII value of lowercase a. So this will create a mapping for that character from 0 to 25, just like we have here. Okay, so for the previous candidate, we want to check, is the absolute difference between the current and the previous less than or equal to k? We know it's always going to execute at least once or twice, because when the character and the previous character are the same, it's definitely going to execute at least in that case. So if that were to happen, we want to keep track of the longest one that we can form here. Let's actually create a separate variable for that. I'm going to call it longest. Initially, we're going to set it to 0, though we could set it to 1. So I'm going to set it to 1 just for fun, because we know at the very least we're always going to include the current character. Like I said, this is always going to execute at least once. We want longest to always be the maximum. So if we find a new candidate, let's try to maximize it. Let's say max of longest plus 1 plus dp of previous. The reason we can do that is because we know that the absolute difference between previous and current is less than or equal to k. And what this tells us is dp of previous is the length of the longest string, the longest ideal string ending at this character so far, like before the current character. So that's why we're adding a 1 here. This is what we had so far, and now we introduce this new character to that, which we are allowed to do. Therefore, we have 1 plus that. Okay, after we're done with this entire thing, we finally found the longest, and we can put it in dp of cur down here. We can say dp, the longest now ending at this character, is going to be the max of itself, as well as what we currently just found, longest. If we wanted to, we don't have to actually maintain the result either. We could actually just return max of dp, whatever ends up being in this array. So if you prefer that, I don't think it really changes the time complexity. So I guess I'll stick with it. It does shorten the code a little bit. So this is the entire code. Let's go ahead and run it to make sure that it works. And as you can see on the left, yes, it does. And it's definitely memory efficient. If you found this helpful, check out Leetcode.io for more. Thanks for watching, and I'll see you soon.